Hello everybody and welcome back to the second video on graph sketching. Last time we started part one and we talked about increasing and decreasing functions. Remember that the result that we had that if a function actually is decreasing over an interval, then the tangent lines to that part of the curve will actually have a negative slope, so f prime will be negative. And if the function is increasing, the tangent lines to that will end up being positive. So we associate increasing, decreasing to a certain derivative that is positive or negative. In a nutshell, that's what we did last time. Today we're going to continue on this, and we're going to be talking about local minima and local maxima of functions. So in order for me to explain that to you, I will ask you to consider the graph of f of x that I'm going to sketch right here. Y-axis, x-axis. Sorry if I squeezed that a little bit together. Those whiteboards are so small, you can't really write anything on them. I'm going to draw a curve that looks like this with a point right here. I'm going to put that in red because it's going to be kind of the focus point of what we're going to do. And this would actually be right there. F of a, right? And that's f of x in blue. That is y equal f of x. Okay, so look at that point. That's the central point of the discussion today, a guy like this. X equals a is actually called, for this function, a local minimum. I think the picture speaks for itself. It's the lowest point around. So if I take a small interval around A, and I look to the left of A, all the y values will be higher than f of A. And if I go to the right, all the y values will be higher than f of A. So we simply, very loosely, should I say, we say that x equals A is called a local minimum. Minimum in the sense of lowest point. Minimum in the sense of lowest point. Okay, good. Now, again, this is Cal, and this is about derivatives, and derivatives are above the slope of the tangent line so many times, right? So let's draw a few tangent lines. Let us start on the left of A. If I draw a tangent line here, I'm going to get something like that. And if I draw a tangent line here, I'm going to get something like this. Those tangent lines, when I am on the left of A, those tangent lines have what sign? Are they positive, negative, zero? They're all oriented this way, right? So they're all negative. Then the slope of the tangent line, which is, by the way, what? What is the slope of the tangent line? We're starting to know this. It's the derivative. This is negative. On the other hand, should I move to the right side of A? So if x is greater than A, let us draw a few tangent lines. So let's draw a tangent line here. Let's draw a tangent line there. Look at these tangent lines. They all have something in common. They all have a positive slope. So ATG, which again is f prime, this time it is actually positive. So on a curve like this, going from f prime being negative to f prime being positive, that is very, very archetypical of what happens at A. Because now let me draw the tangent line at A. Take my red marker marker is about to die on me. No. Look at the slope of the tangent line right there where I have a local minimum, right? So if x is equal to a, then the slope of the tangent line, which again is the derivative, the slope of the tangent line is actually 0. That's going to be an important result a little later on in today's video. Okay, so what can we see from this? Just preparing the conclusion in a minute. If I have a sequence of tangent lines that are all negative, and then following the contour of the curve they become positive suddenly, not suddenly, but like smoothly on the graph, then this transition from the slope of the tangent line being negative to positive, this is actually associated to the fact that the middle point right here is a local minimum. Okay, now let us do a similar analysis. Consider a graph of, let's call it another name, g of x. Let's have a couple of axes, not very straight. And let's have a graph that maybe looks like this. Aha, interesting. Red. Let's call this point the point B. We can see here that the point B is going to be called a local maximum. Why is that? Again, because if I move a bit to the left, all the y values are less than f of b. And if I move a bit to the right, all the y values are less than b. So b is the highest point in a small neighborhood around, well, itself, right? So we can say that x is equal to b is a local maximum. Maximum being, and the meaning of the word maximum here is the highest point. Highest point around itself. So in a small neighborhood, in a small interval around b, f of b is the highest value in that interval. Okay, so let's do the same analysis we did before. Let us draw a few tangent lines, this time to the left. Here's one to the left. Here's another one to the left. What do you notice about these tangent lines that are on the left of B? So we can say that if x is less than b, the slope of the TG line, which is the derivative not of f but of g, so g prime, this time the lines are oriented that way, so they are positive. And if you move to the other side of B, you're going to find the exact opposite. So I'm just going to, if I can do a better job this way, here's a tangent line right there. Here's another tangent line right here. So look at these tangent lines. Their slopes have to be negative because the lines are oriented that way. So if x is actually larger than b, the slope of the tangent lines, which is g prime, are now negative. So it's the opposite of here. The slopes here are actually going from positive to being negative. And when that happens, we associate that to x is equal to b being a local maximum. But that's interesting now, because what happens at b itself? If x is equal to b, then the slope of the TG line, which is the derivative, what is the slope of the tangent line at b? Is there such a thing as f prime at b? No, it's a cusp, so it's not differentiable at b. F prime of b does not exist, so g prime of x, when x is equal to b, that value does not exist. Ha! Okay, time to draw some conclusions from all of this analysis. So first, from the top graph, if f prime changes from what we have here, changes from negative to positive around x equals a. So changes from negative to positive around x equals a, then x equals a is a local minimum, local minimum. Right, like this point here, it also has a tangent line that is 0, of course. We will make note of that in a minute. Also, to conclude this loaded up little whiteboard, if f prime changes this time from plus to minus around x equals b, so from plus to minus. So here the slopes are, in the case of the second graph, the slopes are positive and after that they're negative. Then x equals b, is to be called a local maximum. Is to be called a local maximum. That's the conclusion of this introductory discussion on min and max. Sorry I had to load this whiteboard so bad, but it's nice to have all the info we need on one screenshot if you want. Okay, so we want to kind of box this. I would box it if I actually had the space. I guess I still can, because this is the important conclusion to this discussion so far. Good, excellent. A little definition and we can actually start looking at problems. So let's get rid of this. All right. Okie dokie. So, what do we got here? Little definition to sort of consolidate kind of all the information that we've had so far. A point x equal to c is called a, change colors, critical number. Critical number. Sometimes we say critical point, but critical number is perhaps a little more widely spread as a terminology. It's called a critical number if either f prime at c equal to 0 or f prime at c does not exist. So what does that mean? F prime of c is equal to 0. It means a horizontal tangent line. F prime at c does not exist. What does that mean? It's a cusp, right? So that corresponds to the first graph we saw on the previous whiteboard. That corresponds to the second one, right? Good. So take a look at an example here. Take a look at an example. This is going to be labeled 2.5 stars. So what do we want in that example? We would like to find all critical numbers of a function, simply. So find all critical points or critical numbers. You know what? From now on, Cn, critical number, will do the job. For f of x, what shall we have here for f of x? Something like 5. Okay, so I got a fourth degree equation, x4 minus 2x squared plus 5. I need to find all the critical numbers. What is a critical number? It's a number that makes f prime 0, or it's a number that makes f prime dne. In either case, I need to figure out the prime to calculate the critical numbers. So that actually means find f prime of x. All right, this is an easy function, polynomial. We can go quickly over this. Derivative of x4 is 4x3. Derivative of minus 2x squared is minus 4x. And the derivative of 5 is 0, so I didn't show the steps here because that's pretty straightforward. I will want to know when this is equal to 0 or when this is dne. For these two situations are the situations where I identify my critical numbers. Okay, I'm going to say one thing. It cannot happen. dne here cannot happen. Will not happen in this case. Why? Because dne means division by 0. This doesn't even have a denominator, right? There is nothing under here except 1. So 1 is not 0. This will never be dne because it can never be divided by 0. But can it be equal to 0? Certainly can. So 4x3 minus 4x equals to 0. Shall we solve this? How do we solve this? Take out a 4x. Take out a 4x since it's common to both. X squared minus 1. Ha! Difference of two squares. X minus 1. X plus 1. See, your skills at factoring are put to good use in this chapter. So, what are we going to do with this? We're going to say that 4x is equal to 0, x minus 1 is equal to 0, and x plus 1 is equal to 0. I'm going to get 3 critical numbers. From this one, x is 0. From this one, x equals 1. And from this one, x is equal to minus 1. So I have here 3 critical numbers. So, conclusion, f has 3 critical numbers. What are they? Critical numbers are 0, minus 1, and 1. So that's a introductory level 2.5 star example on finding critical numbers. Easy enough. Easy enough. Good. So let's move on and let's try something perhaps a little more interesting, maybe like a 3 star in these things. So what do we got here? Let's do that in black again. Exemple 2. 3 stars. For f of x is equal to, what shall we have here? X minus 8 plus 1 over x plus 1. For this f of x, find all critical numbers. Find all critical numbers as well as all intervals, where f is increasing and decreasing. So in this example, we'll incorporate some of the stuff we've done in the previous video and some of the new stuff here. Okay, so I guess critical numbers mean what? What does this mean, critical numbers? Critical numbers happen when either f prime is 0 or f prime does not exist. Either way, I know that I have to calculate f prime. So let's do that. What is f prime of x? Well, it's a derivative of x minus 8 plus x plus 1 to the minus 1. What did I do to that little last guy over here? I simply brought it up because I'm going to be using chain rule on this. It's going to save me time overdoing the quotient rule. So it's a plus or a minus rule. So it's x prime minus 8 prime plus x plus 1 prime to the negative 1, sorry, prime. That's a prime. It looks like a 1. Let's do a better job at showing that it is a derivative. 1 minus nothing minus 1, x plus 1 to the minus 2. I'm applying the power rule for function, times the derivative of the inside, times x plus 1 prime. What is this? Well, that's 1 plus 0, so that's 1. So that's 1 minus 1 over x plus 1 squared. Now, you're not going to like this, but in this chapter, we have to simplify our derivatives to a maximum. Otherwise, if we don't, we're not going to be able to extract nicely the critical numbers. So this is all very nice. It's a pretty good DNS answer, but I will want the DS answer. So I will want the answer that actually incorporates a common denominator of x plus 1 squared. So I shall have here x plus 1 squared minus 1. So I shall have x squared plus 2x plus 1 minus 1 over x plus 1 squared. The 1 and the minus 1, that's a minus 1 right here. The 1 and the minus 1 are going to go away. So I have f prime of x equals to x squared plus 2x over x plus 1 squared. And to make one last simplification on this, I'm going to take out an x from the top. And this is our f prime in its most simplified version. That's f prime. That is f prime. Okay, so critical numbers happen when f prime is 0 or f prime does not exist. When in a fraction is f prime 0? In a fraction, f prime equals to 0 when I have, I don't know, when is it 0 in a fraction? When I have 0 divided by a number, right? So what does that mean? It means that the numerator of the fraction is equal to 0. In other words, it means x plus 2 is equal to 0. In other words, x is equal to 0 and x is equal to minus 2. F prime does not exist. When does that happen? When is it that a fraction does not exist? Well, that's the opposite. When you have a number over 0. In other words, when le dénominateur égale à 0. That means x plus 1 squared equal to 0. Take the square root, bring it to the other side. Minus 1 is the critical number coming out of the denominator, while 0 and minus 2 are the critical numbers that are actually coming out of the numerator. So that answers the first part of the problem. We have some critical numbers. Good. So the other part of the problem is to actually try to see if we can incorporate some of the notions we saw in the previous video to find the intervals where f is increasing and decreasing. And for that, we're going to need a little more space. So let's keep in mind the derivative, and let's keep in mind the critical points or the critical numbers. We're going to put these into a table. So you know what? Since I don't have a very good short-term memory, I'm going to save some of that information here. And then I'll erase it when I don't need it no more. So now, to find where f is increasing and decreasing, we're going to do what we did the other day, which we are going to refer to as a table of variation. What is a table of variation? It's a table like we did the other day. All right, that green is dead. Okay, so the table of variation that we had is going to have those three lines. A little longer. And as usual, you're going to go the x value will cover the entire real line from minus infinity to positive infinity. We are going to put here our critical numbers in order from least to largest as usual. So minus 2, minus 1, and 0. And these critical numbers subdivide my intervals like this. Now, who remembers what we did in the previous video? Well, if you're watching those videos back to back, it should be fresh to your memory. Right here, I actually need to choose any number I want from negative infinity to minus 2 and throw it back into f prime and determine what sign comes out of that. So what shall we take here? Moins 3. Shall we take minus 3? So f prime of minus 3. Where's my f prime? It's here. So minus 3 times minus 3 plus 2 over minus 3 plus 1 squared. This is how we do this. We can actually get rid of that. So again, the answer to this number-wise is not important, but we would like to know the sign. So minus, minus, and the bottom is always going to be a plus because it's a square. So that is going to be a minus and a minus over a plus. It's going to be a plus right here. And we continue. Here, minus 1.5. Minus 1.5. We put it in. Minus 1.5 minus 1.5 plus 2 over something that I don't really care what it is because it is positive. And why is it positive? Because the bracket has a square. Alors, it's a minus times a plus. It's a minus times a plus. Between minus 1 and 0, let's go with minus 0.5. F prime of minus 0.5, and something a little strange is going to happen here. So minus 0.5 times minus 0.5 plus 2 over, once again, something that is positive. Yo, that's a minus times a plus. That's a minus. That's a minus. Look, the signs don't change around -1. Interesting, isn't it? Or not. Between 0 and infinity, we pick up 1. I'm going to save you the trouble because basically it's just calculation. This one turns out to be positive. Now, what do we actually have from here? Remember the result this time from the previous video. If f prime is positive, the function is increasing. If f prime is negative, it is decreasing, and it is increasing. And now for the conclusion, to incorporate the result that we had in the previous whiteboard, what happens when f changes from going up to going down? So from f prime going plus to f prime going minus. What do we have here? We have a local maximum. Let me get rid of these little values that I don't need no more. Because now what I would like to write is that this guy is a local maximum. This is finished. Local, don't go away. Local maximum. Why? Because here the curve goes up, 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 and then the curve goes down, 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 down. So that point is a point right on top of the curve. It's a local max. Here, the curve goes down, 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 and it keeps on going down. There is no change in increasing to decreasing. There is no change in the sign of the derivative. So that is nothing. That point is neither a max nor a min. But 0 is something, because f prime is negative, the function goes down. F prime is positive, the function goes up. What do you call a point at the bottom of the curve like this? You call it a local min. So, as a conclusion, f has a local maximum. We're just going to state it as like x coordinates. Local max when, or I shouldn't say at, because at probably means both the x and the y component. I will just say when x is equal to -2, and f has a local min when x is actually equal to 0. Sorry, not -1, but 0. 0. And that would be the conclusion of this problem. So it's a more comprehensive problem than before in the sense that we were not given those numbers, we had to find them, and once we found them, we have to make the table to decide what goes up, what goes down, and where are the local min, where are the local max. To finish, I can also say that f is increasing on -infinity to -2 union 0 to infinity, and I can actually say that f is decreasing on the interval -2 to 0, and now we have a complete picture of what is happening with this function. You can see that with all this information, when comes the time to sketch the graph of this function, it's going to be easy. Okay, enough for one shot. So I wish you well. I'll see you with more graph sketching next time. Take care.